Since the next assessment report 6, is being released, and the physical basis executive summary summary for policymakers has been released in its final form, I thought I'll run through those. We have already looked at some CMIP 5, CMIP 6 comparisons, some CMIP 6 projections, and so on. This is just to highlight some of the slightly different ways in which AR6 is reporting things compared to AR5. This we looked at, of course, so this gives you a longer term perspective on how the warming is happening. So warmest multi-century period in more than 100,000 years. So this is where the warming has occurred since the Industrial Revolution compared to the period from Common Era year 1. So 1 to 2000 is constructed here, and there are instrumental records, and the constructed temperature is overlapped a little bit here. And here are again our attribution exercises with all the forcings and just natural solar, solar and volcanic forcing, which just re-emphasizes the previous results. This is the observed warming from 2010 to 2019 relative to 1850 to 1900. So that gives you a sense of just how much we have warmed recently. So each decade is warmer than the previous decade, and the warmest years on record are happening again and again every other year. And they are happening in non-El Nino years. Remember, El Nino creates a mini global warming, so when the warmest year occurs in El Nino, people tend to say that's not surprising because El Nino adds to the global warming. But it's even now La Nina is happening in 2021, and yet temperatures are very warm because La Nina should actually produce a slight cooling at global level. So contribution to warming based on two complementary approaches: aggregated contributions to 2010 to 2019 warming relative to 1850 to 1900 assessed from attribution studies. So you are looking at the warming here from total human influence, well-mixed greenhouse gases alone. Other human drivers like land use change are creating a bit of cooling, so this difference here is included here. Solar and volcanic drivers are very small, and internal variability is also relatively small compared to the total warming, which means we can attribute the warming to human influence with complete confidence at this point. Contributions to 2010, again this contribution to this warming 2010 to 2019 assessed from radiative forcing studies. So carbon dioxide, methane, nitrous oxide, halogenated gases, HFCs, and so on. Nitrogen oxides cool a little. Volatile organic compounds and carbon monoxide warm a little. Sulfur dioxide, organic carbon, ammonia, black carbon is got a significant range, but it's on the warming side. And land use, reflectance, and irrigation are creating a slight bit of cooling, and aviation contrails are adding to the warming, and this is something to watch out for in terms of how it will grow. So you can see how the radiative forcing studies and attribution studies are done separately to ensure that we are in fact attributing properly the recent warming. And climate change is already affecting every inhabited region across the globe, with human influence contributing to many observed changes in weather and climate extremes. This is what we said when we opened this chapter with the AR5 map. Here things are done slightly differently. So we are looking at type of observed change in hot extremes. So increase, decrease, low agreement in the type of change, and limited data and or literature. Remember, IPCC synthesizes all the published results and then carries model experiments for future projections. So confidence in human contribution to the observed change is high, medium, low, and low due to limited evidence. So you have to be careful about that as well. So this is the synthesis of assessment of observed change in hot extremes and confidence in human contribution to the observed change in the world's regions. Again, split into North America, Central America, South America, Africa, Europe, including Greenland, Asia, Pacific Small Islands, and Australasia. And I won't go through all of them, but lots of places in the observed change of hot extremes, there is high confidence in large regions, including South Asia, for example, which includes India and its neighborhood. And when you move to synthesis of assessment of observed change in heavy precipitation and confidence in human contribution to the observed changes in the world's precipitation, so increase, decrease, low agreement in the type of change, and limited data and or literature. I just want to point out that there are large regions. As we said before, precipitation continues to be difficult for modeling, for observing, for extracting change with great confidence, and so on. So I just wanted to point out that we have already shown trends, talked about increases in extremes, increases in widespread extremes, and so on, and yet South Asia here comes in as low due to limited agreement in terms of changes in heavy precipitation and confidence in human contribution to the observed changes. And I should again emphasize the multi-decadal changes are a persistent natural variability here, so it's possible that we haven't come out of the multi-decadal variability. And of course the issue is that there may not be enough data yet to look at the modulation of the natural variability by global warming. But extremes are there and impacts are there, so it's a question again of how we assess risks, and this is why I wanted to show this. This is now about agricultural and ecological droughts and confidence. Again, increase, decrease, and confidence levels here. Of course, there is meteorological drought, which is just the deficit from the expected rain, and there is ecological drought and agricultural drought that are based more on soil moisture and water availability for agriculture and impacts on ecology and so on. Again, lots of regions where agreement is low and or data is limited or literature is limited. And coming here to South Asia, it's again a question of having low agreement in the type of change. Okay, so those are the number of studies there that have been looked at. So one has to be careful in terms of attributing or claiming climate change in many contexts, because strictly scientifically speaking, confidence in human contribution may be low, or agreement in the type of change may be low, but this doesn't mean risk doesn't exist, so one has to still continue with risk assessment. Future emissions cause future additional warming, with total warming dominated by past and future CO2 emissions, because CO2 is a long-lived gas that accumulates, and warming is proportional to the accumulated CO2, as we have talked about when we talked about emissions gaps. So future annual emissions of CO2 here, and of a subset of key non-CO2 drivers across 5 illustrative scenarios we looked at, SSPs. So I won't go into too many details, but we have already looked at these. The benign ones are down here, SSP1 1.9 and SSP1 2.6. The others offer various levels of gigaton CO2 emissions per year, with associated million tons of methane per year, nitrous oxide in million tons per year, and one air pollutant and contributor to aerosols, that is sulfur dioxide, in million tons of SO2 per year. So these are, as we said before, delay the control on warming targets. So net zero often refers just to CO2, not the other greenhouse gases, so one has to be very careful about where we are going to hit these transitions into net negative, for example. Without considering these, just considering CO2 can be a problem in terms of expected warming and meeting the global warming targets of 2 degrees centigrade and 1.5 degree centigrade with 67% probability and so on. Contribution to global surface temperature increase from different emissions with the dominant role for CO2 emissions in various SSP scenarios. So again, total observed and CO2, non-CO2 greenhouse gases and aerosol and land use for various scenarios here. So one has to be again very aware of where each of these will lead into the future. And as I mentioned, the scenarios for the first 2-3 decades are dominated by model uncertainties, and once you go beyond 2050 to longer term, the projections tend to be dominated by scenarios. So here we are looking at change in global surface temperatures in 2081 to 2100 relative to 1850 to 1900 when we look at these numbers here. So we start with the observed, and then we look at the projections due to CO2 and non-CO2 greenhouse gases and cooling due to aerosols and so on. So you can see obviously the business as usual scenario or the challenges of mitigation and adaptation that are considered in these SSPs give you very high warming if you don't control the CO2 emissions as we can expect, right? With every increment of global warming, changes get larger in regional mean temperatures, precipitation and soil moisture. So we're looking at observed change per degree C global warming. We have again our warming hole here, which is likely related to AMOC, but there are other theories of volcanic forcing and so on in the observed period. Okay, simulated change at 1 degree C warming. So this is showing annual mean temperature change. Warming at 1 degree C affects all continents and is generally larger over land than over the oceans, as you can see. In both observations and models. So this is the observed change, this is the simulated change, and you can see that the models do not capture this part here. If you look at annual temperature change relative to 1850 to 1900 for 1.5 degree C warming, 2 degree C warming and 4 degree C warming, polar amplification gets stronger and stronger. Global south begins to get hammered by the time you reach 4 degrees centigrade. So global warming will create winners and losers, and the warming hole disappears in the models, remembering that the models are not good at simulating it in the observed period. Okay. Annual mean precipitation we have already seen relative to 1850 to 1900. We have talked about potential increase in rainfall over parts of Sahel, Sahara, over the oceans, Middle East, monsoon regions, and so on. And we have also talked about increase in rain-dominated precipitation as opposed to snow-dominated precipitation over the Arctic, for example. So that is not good news in terms of sea ice loss and so on. And we also have to remember that the models are typically not very great at simulating precipitation compared to the skill in simulating temperatures. But compared to CMIP 5, even CMIP 5 was getting better at simulating regional trends, and CMIP 6 shows improvements in that as well. So this is the annual mean total column soil moisture change. Again, difficulties in simulating soil moisture are similar to precipitation simulations. So here simulated change at 1.5 degrees, 2 degrees centigrade and 4 degrees centigrade. Wetter regions are going to get richer in soil moisture. There are some regions like the Amazonia shows dangerous loss of soil moisture in standard deviations of interannual variability. So relatively small absolute changes may appear large when expressed in units of standard deviation in dry regions with little interannual variability in baseline conditions. So that is something that has to be remembered. Okay. This is just showing, let me stop this podcast here and come back to a few more in the next one, because I'm already up to 15 minutes here. But this gives you a sense that the projections continue with newer scenarios which have gone from totally RCP based scenarios in CMIP 5 to SSP based scenarios in CMIP 6, and some of the renditions of the future projections have been changed as well into agricultural droughts, ecological droughts, and we will see soon return periods of some of the extreme events and so on. Okay.